right, fantastic, good. Okay, so this will be a little bit less technical, hopefully, and give you a flavor for what we're trying to do towards building towards a quantum microscope, actually, which is an intelligent quantum camera as the integral technology that makes it work. I've given the title a little bit of a sexier flavor to appeal to the participants who are not quantum people. So we're going to play with some quantum ghosts, and we're going to try to see how we can see things that might otherwise be very difficult with conventional classical technology. So I usually begin the quantum camera talk by explaining firstly what we know about conventional imaging. So when we take photographs of things, what do we actually do? So maybe I should try to put my pointer on. Let me see if I can do that. So what we typically do is we might have a camera, we're pointed at some scene, maybe a selfie or some background that we want to take a photograph of. And if we get all the conditions correct, then we get a beautiful image. As physicists, we'd say, okay, but what does it mean to get all these things correct? So let me give you the technical language of it, and then I just put it back into simple English. So physicists tend to draw objects as little arrows. We know that we need lenses. Your cameras have all got lenses. Everybody knows that in order to make an image of this object. So how does it work? So what we do is we can take some point on our object, let's say the top of the arrow, and we can follow how the light travels through the system. So it could go straight and then go down, or it would go through the middle or bottom and then through. But in all these cases, that one point arrives at a single point on the other side. So all the rays from this point arrived only to that point. And so now we get this lovely image on the other side. So you would know this by saying that we have a nice sharp image of our object. The physicists would say that what we have is a position correlated system. This means that the positions on this side, the object side, are connected to the positions on the image side. And that's why we can take an image of an object. That's why, lens systems are very good for taking pictures. What if I didn't choose this particular plane? What if I had chosen, say, a plane over here? Well, then one point on the object would map to 3 points on this side. So that's very bad image correlations because one point maps to many. And we also know this in our everyday life. We call this a blurry image. So if we don't get the distances just right, then we don't get a very good system. And that's why if I go back to my system, I can see that there's certain things that I've assumed in this whole imaging process. One is that the light travels from the object to the image. I assume that I get all these conditions correct, the distances, the lenses, and so on, so that one point over here mapped to one point over there. And actually, what I didn't show you, but of course we always assume, is that if I want to take a nice high-resolution image of my objects, I need to have lots and lots of pixels. And what we'd like to do is we'd like to say, let's try to break some of these assumptions. Let's not use a man-made system for the correlations that we need. Let's not have the light travel from the object to the camera. And let's try to take very nice pictures, even though we may not have very many pixels. In fact, we're going to try to take a quantum picture with just 1 pixel, no resolution at all. So how can we do this? Well, what we have to do is we have to swap out all of our classical ways of thinking and replace it with a quantum way of thinking. So in my group, we play with structured light. This means we try to play with photons and photonics and light-based technologies. We do quite a lot of the classical research and applications, but we also do quantum. So what's the difference? Well, here's a classical case where Angela is using bright laser beams, so billions and billions of photons, and she's shaping the light to be whatever she wants. In the quantum case, what we do is we use a little crystal, and if we engineer the properties of this crystal properly, we can produce 2 entangled photons. I'm going to show you a picture of that in a second, where we can entangle them in any degree of freedom we like. And so we do our structured light, but now we do it with 2 entangled photons from a quantum source. And the way we like to think about it is that, light has got many degrees of freedom, and some of these pictures show the spatial degrees of freedom, like, pixels or different patterns of light. These are all properties that quantum light can have. And so we like to call this quantum mechanics with pictures, because it's really just playing with the alphabet of patterns of light to do really cool quantum science. In our lab, the way we do that is we generate from this little crystal 2 photons and we send them to our measurement devices. But in today's talk, I'm going to concentrate only on the imaging aspects. So let's just go away from all this complexity of structured light and spatial modes and the type of research we do. And what we're going to do is we're going to say, we know that these photons are entangled. How can we leverage on that? So let's have a look at what we do actually in the lab. So in the lab, we will take a high energy particle of light, just one particle, and we bring it in to a little crystal. And if we engineer the properties of this crystal correctly, then what will come out on the other side are 2 lower energy photons. So they're lower energy because their energies, when you add them together, give you back to what you started. So that's energy conservation. And they tend to go off in opposite directions. We can engineer them also to go in the same direction, but let's say in this cartoon, they're going in opposite directions. So one photon is going to the left corner of the room, and the other photon is going to the right corner of the room. And these photons are connected in a quantum way. So if I do some measurements on one, it affects the outcome that you're going to see on the other one. They have this connection. So why do they have this connection? It's because when they are born in the crystal, they are born at the same position. So remember my optical system, my camera that I used to take photographs, I got position correlations, like a connection between the object and the image plane, by engineering the lens and choosing the distances very carefully. But here, my 2 particles of light are already connected at their birth. They're connected because they're born in exactly the same place. So what does this mean in terms of utilizing them for imaging? It means that their positions are correlated. In simple English, what this means is if you know the position of one, you can work out the position of the other one. So let's zoom into these 2 streams of photons, particles of light, and let's look what happens. So we'll use our little magnifying glasses and we'll zoom in. And what we're going to see are 2 things. I'll play the animation twice. In the first case, what you'll see is the random arrival of each photon. So if you watch just one of the magnifying glasses, you'll see that the arrival of the photon is completely random. You never know where it's going to arrive. You don't have any control over that. On the other hand, I'll play it again now. If you watch the 2 magnifying glasses together, what you'll see that if you know where the one photon arrived, you can say something about the arrival place of the other one because they are correlated. So if this one arrives over here, that one arrives in the same place on the other side. So we have these position-connected particles, and now we can use that for quantum imaging. So what we will do is we again have our crystal. This time it's shown a little bit more technically, and we have our high energy light coming in, and we're going to produce these 2 photons, photon A and B, and they're going to go to opposite ends of the room. And what I'm going to do is I'm going to place an object in the path of one of the photons. Let's say photon B. So photon B is going to pass through this object. And now I'm going to collect that light with a big bucket. And what I'm doing in this case is I'm ensuring that I collect the light in an aperture or a detector that's much bigger than the object. This means that this photon B, doesn't know anything about the object, nothing at all. Why do I say that? Because imagine I had 2 different types of objects, and I had my black Koki, and I blocked out in black everywhere I don't want the light to get through, so it can only get through the white parts. We see if I collected one photon, I wouldn't know if it was through a ghost or a triangle, and the second photon and a 3 photon. All I know is I get a click if the photon gets through. But because the detector is much bigger than the object, I don't know what the object actually looks like. So I've got no information of the object. What about particle A? Well, here I'm going to put my camera. Now, photon A never saw the object. So photon A also doesn't know anything about the object, and it's going to go to the camera. So try to picture the situation. 2 photons are going to opposite ends of the room. The one passes through the object, but I collect it in a way that it knows nothing about the object. And the other one, which has never seen the object or interacted with it in any way, goes to the camera. So neither photon has any information about the object. So what do we see on the camera? So as you watch the video, look for two things: the random arrival of the photons, because quantum is a very random process, but because these photons are position correlated, together they can form an image of this object. So here you see the photons arriving on the camera, very random, takes time to build up, but as it builds up, I think you can clearly see that we have an image of our little ghost, which was in the path of the other photon. So the camera sees this kind of ghost image of its quantum partner. And this we call quantum ghost imaging. It's actually been around now for about 30 years. Yan Hao-Shi was the first person to demonstrate it. And actually, he didn't set it up to do imaging. He set it up to do some probing of really fundamental quantum questions. But in the process, it became this really cool imaging technology. And since then, it's been used for many, many things, lots of applications, from fundamental physics all the way to biosensing. And we've written a little commentary about this to explain its history. Okay, so what we can see now is that on our camera, we have an image of the object. And in fact, we have broken already one of the assumptions, actually two of the assumptions in our original statement. The light from the object never traveled to the camera because the camera photon never saw the object. And we don't have any fancy lenses or distances in the system. It's not our optical system, our beautiful lenses on our cameras that are making it possible to image. It is the quantum correlations that nature gives us just directly from the entanglement. So entanglements can be harnessed for this lovely application. We can also exploit other properties of these photons. So this was all position. In physics, we talk about momentum, but you don't have to worry about it. It just means that I can get an upside down image if I use a different degree of freedom. But it still works, and we can see images of objects. So what makes it work, in fact, is this idea that we have to measure these two photons together. If we don't measure them together, then we don't know which photon is tagged to its partner. So we kind of lose the information of the entanglement. And so the key in all of this is a really good stopwatch. It's a way of finding these entangled photons in a sea of unwanted light. So quantum optics experiments involve what we call measurements in coincidence, which means just a really good timing system to tag the arrival of these photons. In our lab, we can understand what's going on in all of these quantum experiments by doing a very simple classical experiment. This is an idea that came from Klitschko. He was a Russian physicist. And what he said is, look, why don't you imagine one photon, the photon A, traveling backwards in time, bouncing off the crystal, then going forward in time in the path of photon B. So it would look something like this. It would be like a laser coming down the one arm, bouncing off the crystal as a mirror and going to the other detector. And he said this would be a very good way to mimic what your quantum experiment is doing, because it has all the hallmarks of entanglement. And in fact, it's true, if we do those experiments, it's in fact how we align our experiments up. We can see here is the quantum image, and below are two classical images, so we can actually simulate experimentally all the things we see in the quantum lab. So we can understand why it's working and not just treat it as some magic or some spooky action at a distance. Okay, what we want to do next is we want to get rid of the camera, because the camera has still got many, many pixels, and we'd like to image without this idea of pixels setting the resolution. So to do that, we think about how do cameras work. And the one way to think about them is that, okay, look, a camera's got many, many pixels. So I can imagine the way it works is a cartoon mathematical equation that says, let's count, this is what C1 is, count how much light arrives in the top left pixel. And then add to that how much light, C2, arrives in the bottom right pixel, let's say. And how much light arrives in the top right pixel, and so on. Let's just add the contribution of every pixel. And you might say, okay, that's fine, but why is it interesting? What value does it give you? Because if you think about it in this like abstract mathematical way, then you can say, oh, but instead of just imagining one pixel switched on, why don't we switch half the pixels on? Because if I switch half the pixels on in a random way, then there's no confusion between this half and this half. So these are kind of random on-off pixels where if I look at the kind of overlap between them, it's zero. In other words, they have nothing in common. This also makes a very nice mathematical statement that if I just add this random contribution to this random contribution to this one and so on, I can also build up an object. And so that's what we do now. What we're going to do is we only have to measure these numbers, which means a single pixel, and we're going to illuminate with these random masks our measurement system. So this is what it looks like in the lab. Again, we have our crystal. We have this high energy photon coming in, and we're producing two entangled photons going out. And this time, we're going to have a single pixel detector instead of a camera. We're still going to keep our bucket detector on the other side, but we're going to have a single pixel detector. We'll load our object on one side like we did before, but on the other side, we're going to use some digital technology just to randomly go through these different patterns, random masks. And then each time we have a different mask, we're going to add up in the single pixel how much light arrived and multiply it by that mask. If I do that, then this is what happens. As I change the masks, I just count the light that arrived in the single pixel, multiply it by the mask and add them up. All right, so you just add them up, and then you can reconstruct an image of the object. So now we have a single pixel as our detector without any camera. You can imagine that that's much cheaper and much faster. And the digital technology used to do the masks, you can get very cheaply out of any data projector for about $100. So very, very cheap technology. All of these were what we call amplitude. It's like saying, wherever it's white, you let the light through. Wherever it's black, you don't. But we can also put something inside the white part. We can put what we call a phase, but you can think of it as like some invisible material that slows down the light. So if we do that, the light will slow down inside this region and would be very fast outside it. And so we can actually detect that. And so this is an experiment where we have this very complicated object. If you look at this bottom panel here, we have an object that's got an amplitude. That means that we let the light through in some places and not in others. But inside the object, these colors that you see are very complicated delays of the light. And we can reconstruct those delays. So we can see kind of invisible things inside these objects. And this is very useful for biological imaging. We can see the structure inside, let's say, a cell, rather than just know that there is a cell there. It's a very powerful technique to look inside for invisible things. So this idea of invisibility was in the title of my talk, and we can go one step further to do something very strange. So far, everything I've shown you, you could have still done with your normal smartphone and the camera that it's got. You could just have taken images. Normally, you wouldn't have got any quantum advantage. So what is the quantum advantage that we have here? So let's go back to the crystal. And this time what we're going to do is we're going to change the color of the two photons that come out. So instead of having them at the same color, which is what I had before, I'm going to make one of them visible and the other one in the infrared. And why is that interesting? Because I'll send the infrared photon to the object. And what I can do is I can put this object, let's say, behind some tinted glass. So we know that we can't see through tinted glass with our eyes. Why not? Because visible light doesn't penetrate it, but infrared light does. The same with your hand. You can't see past the skin inside your hand with your eye because visible light doesn't penetrate the skin, but infrared light does. You can see deeply into living tissue. Now we can penetrate very deeply into structures and see invisible things, but then put them onto a visible camera. So that's exactly what we've done, and here's an image of the object. The image is taken on a visible detector, but the invisible photon is going through to find these invisible objects. And if you look at the images that we're getting, you can see that they're a little bit noisy. So quantum actually lends itself very, very nicely to machine learning and AI, because what we can do is we can feed these very noisy images through a neural network, and instead of having beautiful images, we can go towards recognition of objects. So here on the left is a quantum image where we have stopped the experiment very, very early. So we cannot easily recognize what it is, but the neural network tells us actually it's the number 9. So we can do recognition of objects by illuminating them with quantum light at very, very low light levels and still know what they are. And so that's what we've been doing. We've been using AI and machine learning to improve and to recognize and to reconstruct quantum images of objects. And the idea is that we can take in rather noisy data, pass it through the system, and come out with either a click of what it is or something that's denoised to the level that somebody like a human could recognize what it is. And so our quantum camera now runs 30 times faster than when we started. And when we started, it was the same as everybody else's. So a very beautiful but slow process. Now it's still beautiful, but much, much faster. And that's the direction we've been going. It's to blend AI and quantum, because quantum produces data, and AI is fantastic, but needs data. It doesn't produce its own necessarily. It needs to feed off other systems to learn from. So we can use it very easily to use our data that we produce. So in the last example, I want to again break even further away from this idea of pixels. And maybe it's a little bit strange, but we can ask a simple question. Why do we even use pixels for our imaging? And you might say, but what else could you possibly use? Well, the idea is that you could use any spatial basis. So you could use patterns of light to try to describe the pictures that you see. So the random pictures I showed you was a type of pattern, but I can use actually more sophisticated patterns. And if you go to astronomers, they talk about the resolution of two objects. How close can you bring two things together before you can't tell them apart? Well, if you use pixels, there's some limit, but actually you can actually extract more information if you use a modal basis. And so the idea that came around about 10 years ago was to say, rather than image with pixels, why don't we try to create images using patterns of light? Look at these two exotic patterns. If they have nothing in common, I can also add them up and make an image of an object. And I won't go through the technical details, but that's what we want to do. So we want to go back to what we started with, which is structured lights. And instead of imaging with our positions, let's image with these patterns of lights. So we had our correlations to begin with, and we're going to replace the positions here with different patterns. And you might say, but okay, how can patterns help you to form an image of an object? Well, it's kind of like this. We're going to take our object, and instead of adding up how much light appeared in the top pixel and how much light appeared in the bottom pixel, we'll say how much light appears in this pattern and how much light appears in this pattern, and so on. It's the same recipe. It's just that we have a different way of calculating and adding up the summations. And when we do this, we call it taking pictures with pictures. We find that we can do much, much better than you could with using pixels. So this is what the quantum experiment looks like. I've always been showing you cartoons, but I thought I'd show you one example of a real experiment. So here's the laser and the crystal, and off the two photons go to two different detectors, and now we can display anything we want. And here's the object. This would be the usual approach of using like a type of pixel basis. And here is what we call the modal approach, which is using patterns of light. And so now we can really speed things up. In fact, we can reduce the number of measurements that we need by another factor of 10. So all of this is towards different ways of thinking about quantum imaging so that we can speed things up and take as few measurements as possible with quantum light to recognize what we're looking at. So I'll end with one last example, which is, is it possible to do this type of imaging with completely independent photons? So in all the examples I've shown you, the two photons I used were created together at birth at the crystal. But could I have two independent photons? That would be like having two torches, one in my left hand, one in my right hand. I point my right-hand torch at the object, and I point my left-hand torch at the camera, and I want to see an image of the object. Well, obviously, it's not possible to have two independent things talk to one another. But what we can do is we can do like a little measurements in the middle by getting them connected. And I won't go through the details except to say that we can do measurements to connect two independent photons so that we can really do imaging with completely separate sources of light. So if we have an object on this side, we can form an image, and we can do it in a different way and get an even better image. So it's possible to do it with independent sources. And what that allows you to do is to move into interesting applications. So where we're going with all of this to wrap up the talk is that we want to have an intelligent quantum microscope that can image very deeply into tissue. And with the independent photons, we want to show that we can do quantum secure data exchange. We have a system where the bank can send one of these photons to the customer. The customer illuminates that photon with their object, and then the bank immediately sees an image of that object. And if you look at this little cartoon, how does the communication work? The bank sends one particle of light to the customer. The customer never sends any information to the bank. So this is fundamentally secure. It's a very good way to communicate in the future. Now, I want to end with a last example because these are the types of technologies and applications that we're working towards. This is where we want to go with our quantum strategy to convert science into technology. But of course, along the way, it takes some time to walk this road and to make practical devices. But it doesn't mean that you can do nothing worthwhile or useful as you work towards your objective. So here's an example of what we call quantum-inspired solutions for locally relevant problems. So what we're really doing in the quantum lab is we're taking photographs in the dark because we have these single particles of lights, very, very few lights. And we're taking these very, very sophisticated images at different colors, trying to reconstruct images of objects with very few photons. And that can be very useful in the real world. So unfortunately, this is a very dark picture in a car of two gentlemen who hijacked this car. Now, unfortunately, it's a murder scene. And what we could do is we could use all the skills that we've developed in the quantum lab to assist the government, in fact, the National Prosecuting Authority, to solve a little riddle that was related to this case. I can't give you all the details, but we could solve that riddle because we had all the skills and expertise that we developed in building the quantum technology, even though this was not a quantum problem. So we call this quantum-inspired solutions. It is the value that we can add to society as we walk down this technological roadmap towards our quantum future. So the value add can be today and not just tomorrow. So on that note, I'm going to wrap it up. I always thank my team and, of course, all the funders, including SAQT. And thank you very much for listening.
Here's a question from Ronald Rahuasha, saying, could quantum imaging be used in combination with AI to study materials and also design more sustainable materials?
It definitely could be used to analyze materials. So quantum imaging, I've been showing you of rather large objects, but you can also do it in the near field to do small objects. You can use it not only for imaging, but also for sensing. So you could sense particular properties of materials. So definitely, as a diagnostic tool, it can be very, very valuable.